Chemical Kinetics. I know, the name alone sounds super complicated, right? With all its rate laws, orders, and confusing graphs. But what if I told you it's actually one of the most logical and, yeah, high-scoring topics in all of chemistry? Let's break it down together.
Think about this for a sec. Why are some chemical changes, like an explosion, basically instant, while others, like a nail rusting, seem to take forever? Well, the answer to that question is the entire point of chemical kinetics. It's just the study of how fast stuff happens in chemistry. That's it. It's all about speed.
And I totally get it. You open the textbook, see a page just packed with formulas, and your first thought is probably, oh great, another chapter I just have to memorize. We've all been there, right? Just cramming info to get through a test without really getting it. But here's the secret. The reason it feels so hard is that it's usually taught completely backwards. Textbooks just throw all the equations, the whats, at you before they even explain the story, the why. And your brain needs that story, that context, to make the math make sense. Today, we're going to flip that script. So let's jump right into our first big hack. I call it the speed story. The whole key here is to change how you see a reaction. Forget about abstract things like A goes to B. Instead, picture them as real things happening right now at a certain speed. Let me break this down with a super simple analogy. Imagine you're making noodles. When you drop them in hot water, they start to get soft, right? They don't just poof and become soft in a flash, and they don't stay hard forever. They're changing from hard to soft at a specific speed. That is exactly what's happening in a chemical reaction. And that speed, that's what we call the rate of reaction. That formal definition you see on the screen, it's just a fancy way to measure how fast those noodles are softening. We're just measuring how much the amount of something, its concentration, changes over a certain amount of time. That's all it is. So let's actually try this. Imagine a problem where reactant A drops by 0.2 m in 20 seconds. Okay, first step, we find the rate for A. That's just 0.2 divided by 20, which is 0.01. Simple. But now, listen up, because here is the crucial part that trips up everybody. See the equation on the slide? It says 2A. That 2 matters a lot. To get the overall reaction rate, you have to divide the rate of A by that number, by 2. Please, please, do not forget that step. All right, let's move on to our second hack. This is where we tackle the part that usually gets people stuck, the rate law. Think of this as a puzzle. We're just trying to figure out how the amount of our ingredients, the concentration of our reactants, affects the speed of the whole reaction. So, this is the rate law equation. I know it looks a little intimidating, but let's just pull it apart. K is just a number called the rate constant. It's unique for every reaction. The real power here, the real secret, is in those little letters, X and Y. These are called the orders of the reaction, and they tell you exactly how changing the amount of A or B is going to change the speed. Now listen very, very carefully, because this is probably the single most important rule in this entire chapter. You absolutely cannot, I repeat, cannot look at the balanced chemical equation and guess what X and Y are. It's impossible. These numbers, the orders, can only be found by doing experiments and looking at the data. Never, ever, ever guess them from the equation.
So, how do we find them? Well, you'll always be given a data table that looks something like this, and your job is to be a detective. The trick is to find 2 experiments where only one thing changes. So, let's compare experiment 1 and 2. See how the concentration of B stays the same? It's 0.1 in both, but the concentration of A doubles from 0.1 to 0.2. Now, what happened to the rate? It jumped from 0.01 to 0.04. Whoa, it got 4 times faster. And that right there reveals the pattern. We doubled the concentration, so X is 2, and the rate went up by a factor of 4. So you just ask yourself, 2 to the power of what equals 4? The answer is 2, right? That means the reaction is second order for A. Now let's do it for B. Look at experiments 1 and 3. We double B, but we keep A the same. And the rate? It doesn't change at all. So that means the reaction is 0 order for B. It's really just a pattern recognition game. Real quick, just a very important point here. Don't get order, which we just figured out from data, confused with this other term, molecularity. Order is experimental. It can be 0. It can even be a fraction. Molecularity is just a theoretical idea. It's just counting how many molecules smash into each other in one step. They are not the same thing at all. Let's move to our third and final hack, becoming a graph master.
This is your visual shortcut to getting easy marks because each reaction order has its own unique graphical signature. If you can spot these patterns, you can answer questions in seconds. For a zero-order reaction, it's super simple. If you just plot the concentration of your reactant against time, you get a perfect straight line sloping downwards. So if you see a graph of concentration versus time, and it's a straight line, you know immediately it has to be zero order.
Okay, now for first order, there's a little trick. Plotting just concentration versus time will give you a curve. But if you plot the natural log of the concentration, ln(a), against time, that will give you a beautiful straight line, again, sloping downwards. That's the signature of a first-order reaction.
And finally, for second-order reactions, the trick is to plot the reciprocal, so that's 1 divided by the concentration versus time. When you do that, you get a straight line. But check this out, this time it has a positive slope. It goes up. So each order has one special plot that makes a straight line. That's your key. This slide right here, this is your ultimate cheat sheet. Seriously, take a screenshot of this, write it down, whatever you need to do. It puts everything we've talked about, the rate law, the linear graph, and even the half-life, side by side for all 3 orders. Having this one-page summary is an absolute game changer for studying. So we've pretty much mastered the what and the how. But to really understand this stuff, we need to connect it all back to the why. Like, why do things like temperature and concentration even matter? What's actually happening with the molecules?
Well, it all comes down to something called collision theory. For a reaction to actually work, 3 things have to happen. First, the molecules have to physically collide. Makes sense, right? Second, they have to smash into each other with enough energy. We call this activation energy. And third, they have to hit each other in exactly the right orientation, kind of like 2 puzzle pieces clicking together. Only when all 3 conditions are met does a reaction actually happen. Okay, we have covered a ton of ground, so what does this all mean for you? How do you take all this information and turn it into success on your exams? Let's talk about a clear, simple game plan. Let's just do a lightning-fast recap. 1. Rate is just the story of a reaction's speed. 2. The most important rule ever, reaction order comes from experiments, never from the balanced equation. 3. Know those 3 straight line graphs by heart. They're your key to identifying the order instantly. And 4. For a reaction to work, collisions need enough energy and the perfect angle. So you see, the big secret to chemical kinetics isn't about memorizing random formulas. It's about understanding the story of speed. And once you see it that way, the whole chapter just clicks and starts to make sense. You've totally got this. So the only question left is, what will you master next?